All right, last section, 3.7. We're doing transformation of polynomial graphs. Now, this is going to spin off of, if you think back to when we were doing x squared, because we've done enough for quadratics that we're good. But if we were doing x squared, what happened if we did x minus 1 squared? What did that do to the graph? Yeah, this moved it one place to the yeah, because we're going opposite horizontal, right? If it's on the inside, you move it one space to the left and right, but you go the opposite way you think, because -1 is to the left, so when we move it, we're going to move it one space to the right. And if we put a +3 out here, we move it one space to the right, and we move it 3 spaces up, right? Okay. With polynomials, it works the exact same way. Doesn't matter what it is. Now, the only thing that's going to be different is the basic shape of it. That we know if we do x squared, it's a parabola, right? Okay. So when we're talking about polynomials, now we're not going to go past, we'll do like x to the third and x to the fourth, because after that, they're all just the same thing, just variations slightly of that one. So when we talk about x to the third, your basic shape of x to the third is going to be this. This half of the graph looks just like x squared. That's going to come down. We're going to have this parabola shape that's here. But on x squared, when we squared a negative number, when we got here, if you square a negative number, it always makes it positive, correct? If we cube a negative number, it's still negative. So instead of it turning and going up like it would be in x squared, it's going to go and turn down, something like that. Okay, so there's your basic graph of x to the third. Again, still going to go through 0, 0. And it's pretty much, it's not quite the same, but it's basically a parabola that's here. And instead of turning and go up this way, now it's just going to turn and go this way because now the numbers are negative. Yeah, so on the top part, we were just going back and reviewing x squared. And anything on the inside of the parentheses makes it move left and right. Anything on the outside makes it go up and down. Okay, and again, that's some of those things that we'll keep coming back to that every so often. When we get to a couple sections down the road, when we start doing some different things, it'll be the same thing. When we do exponentials, it'll be the same kind of thing when we go through exponentials. So it's the same thought process. We'll just change what the graph is when it comes to it. All right, and the other big graph that they're going to look at in section 3.4 is x to the fourth. And the only big difference between x to the fourth and x squared, now, if you still remember the end behavior is still going to be the same. Because if it was anything to an even power, they're either both ends up or they're both ends down. With x to the fourth, it's a parabola shape, but it's a flat bottom parabola that it's going to come in, and instead of curving in more like a U shape, this is going to be like it's going to be exaggerated U. It's going to look more like that. And the biggest reason is that when you're inside of 1, if you think about it, like if you're inside of 1, what happens if you take a half times a half times a half times a half? What does the number keep doing every time you half something? Yes, like dividing by 2, right? So it just keeps getting smaller and smaller and smaller and smaller. So when you stay inside of from 0 to 1, if you keep multiplying a fraction by a fraction by a fraction by a fraction, it keeps getting smaller and smaller and smaller and smaller. So those numbers that's close to 0, they're going to get really flat. But then once we get outside of 1, then the numbers are going to take off in a hurry. So it's similar to x squared. It's just the bottom part's kind of an exaggerated, flattened out part. It may not be quite that much, but we're just, for graph wise, that's kind of the image that you want to have. That if we were to put x squared on top of that graph, x squared would look more like this. Actually, probably would kick out more like this. Probably be more like that. Probably get out wider as this thing tends to go up there. Because x to the fourth, once you get to the fourth power, once you get past 1, now you're doing, bless you, now you're doing 2 to the fourth power instead of 2 squared. So this thing will go up a whole lot faster than x squared would. But in the beginning, it's going to kind of look something more like that. And again, it's not the best graph in the world. I kind of messed that one up a little bit. But that's kind of the idea of what you want to think about as far as where it goes there. Okay, and a lot of what you're going to do in this case is they're going to give you some different graphs, and they may not even ask you to graph it. They may just ask you, okay, if these are our two parent functions we have, and they tend to call these parent functions because this is x to the third and x to the fourth. And if you do x to the fifth, it looks really similar to this. If you do x to the sixth, it looks really similar to this. The only difference is, again, it may just get flatter and flatter as you get close to the bottom here. This one, same thing. It may bottom out more if you do x to the fifth. It may be that when you get here to the beginning, it may be like flat like that, and then start to turn and go something like that. So it just, in the middle, it's going to flatten out a lot more. Is really what it comes down to when you make those powers. But anything x to the fifth, x to the third, x to the seventh is going to look something like that. X to the fourth, x to the sixth, x to the eighth, they're all going to have that kind of very exaggerated flat bottom that you've got here. Okay, so they're going to ask you to do something like this. How do transformed graphs compare to the parent function? So you may have something like this where you got 3 times x to the fourth minus 18. Okay, and again, when they're talking about the parent function, you're basically saying, all right, we've got x to the fourth. That's kind of the parent function because we've either got x to the third or x to the fourth. With this section, that's pretty much the two things they're looking at. Okay, so we know we're talking about x to the fourth. So then it's basically saying, all right, so what happens? What do these other numbers outside of x to the fourth do? What does that 3 indicate there? If it's a whole number that we multiply by, does anybody remember what that one is? It's a blank of 3. Yeah, there we go. We're getting close. Not expansion. They do expanding, but they use a different word instead of that. Take the rubber band and you. There we go. We got stretch, right? So in that case, that would be a stretch of 3. Or a stretch scale factor of 3, something like that. Basically, the big thing is you're stretching it out. If it's bigger than 1, it's a stretch. If it was less than 1, compression. Yeah, there we go. So right thought process, just got to get the right word. So stretch is where you're greater than 1. If it's between 0 and 1, then it's a compress because you're packing this thing down there. And then the minus 18, that's going to be 18 to the up, down, left, right. That's on the outside, correct? There is no parentheses. So that's going to be your up, down in that case. And if it's negative, then we're just going to go 18 down. All right. Now, the good thing is I'm not probably going to ask you to do, if I do graphs with these, it's probably going to be more multiple choice just because these get to be a little bit, kind of funky. But if you wanted an idea of what the graph would look like there. If we did x to the fourth, and that might, again, I'll exaggerate a little bit because it's almost an exaggerated flat bottom part of it here. And we'll do that just so we know it's not x squared. So it's an over exaggerated kind of bottom part of it there. Almost looks like a flat bottom boat. Anybody's does any kind of get out the boat, not a speedboat or not a yeah, it's like the cheap versions you can get. That's just like a U-shaped boat that's just flat on the bottom. It's got some sides on it. That's kind of what you want to think about there. Okay, so if this is x to the fourth, for x to the fourth minus 18, again, you're going to drop this thing down. Let's say this is, 10 and this is 20. Then you would drop it down here, or kind of flatten out, do something like that. But then because it's scale of 3, it should be on the inside of this graph. So it would be something kind of like that. Because again, if you're stretching it out, now instead of being wider, now it's going to be a little bit narrower. So it's going to stay on the inside of the shape that we're looking at. Okay. But again, I'm not going to ask for like tons of details on these. So this will be more one of those things of just probably more like the multiple choice in this kind of thing.
Where'd you get that second one from?
Oh, this was if we were just doing x to the fourth, that would be this line up here. And then because we're going to go 18 down and then stretch of 3, so now we're going to drop this graph down 18 spots. And because it's a stretch of 3, it's got to be a little bit narrower when we're going through this.
So stretch it, is it like up and then over?
Stretching, it's more like a narrowing kind of thing. It's almost like the slope. If you had a line that was like the slope was kind of wide, now it would make it go wide. Yeah. If you got a fraction, that's going to make it go out wide. So a whole number, anything bigger than 1 is going to make it be narrower. Anything where it's like a fraction, it's going to make it be wider. Okay. Yes. What's that? Really, it's the last 3 sections, but really it's everything in the first half also, because you got to know synthetic division, which was section 4. You've also got to know some operations of just adding, subtracting, multiplying, which was section 2. And then, let's see, I'm trying to go through. 1 was just naming it, so that's standard form, so you kind of have that one. So really, it's a little bit of everything when it comes down to it. Yeah.
So what I was asking was when you actually have to plot the points
Mhm.
on the graph,
Oh.
you put the 3 over 1, so you go 3 over 1?
Well, now in this case, it's going to be multiple choice, because with it being x to the fourth, there's not really, the shortcuts we had before, like we were talking about, you could do that with x squared. It doesn't really work with x to the fourth because the powers get it's such a big power that the impact is there. And so this would be one you'd almost have to plot each individual point to see exactly what it would be. So, yeah. So this would be one, it'd be multiple choice. Basically, it'd be one of those where I would just say, find the graph of this one, and it's just A, B, C, D. And the big thing is that, so it would be one of those where I would have one that would be 18 down, 18 left, 18 right, or 18 up. So all you'd have to know is just which way do I move the graph, kind of thing. So you're not going to have to plot points, because it'd be one of those where it'd be extremely obvious as which one it is. And I'll pull one up in a little bit and show you. Okay. All right, so let's do an x to the third here. Let's do x minus 2 to the third plus 4. All right, so we've got x to the third. We've got a minus 2 and a plus 4. So it just comes down to the 2 and 4. What's the impact with the 2 on the inside and the 4 on the outside? What do those two numbers do? Yep. 2 right and 4 up. Okay. All right, now what we'll do, and I'll just kind of do this very lightly. If we're doing x to the third, and we didn't do anything to it, x to the third will look something kind of like that. Again, just doing it so you can just very, very, very lightly see what it is we're doing there. So all we're going to do then, and again, this is all you're going to do, and it will be x to the third. That would be easier to graph just because of the way the numbers are set up. But even for this one, it would probably still be multiple choice. That if we've got this part of it, we're going to move it 2 spaces to the right. and then 1, 2, 3, 4 spaces up. And instead of the center being at 0, 0, now it's here. So then that graph is going to have that same basic shape. So it would look something kind of like that. Okay, and if it's a good multiple choice question, they should have this point marked so that you've got a reference of exactly how much we moved it up, down, left, right, so you can kind of see what's going on. Without that point, it's a little more difficult. But again, this would be one of those things where an easy multiple choice question is that we would have this graph here. I have another graph that would be here, have another graph that would be here, and another graph that would be there. And it basically would be, this would be A, B, C, D. Pick the right one for where the graph should be. So it's a combination of 2 up or 2 right and 4 up, or 2 right and 4 down, or 2 left and 4 up, or 2 left and 4 down. So that basically we'll just move the points, up, down, left, right, and you just have to pick the correct one. So that you don't have to worry about getting specific points. You just need to know which way the graph is going to move for those. So does that help a little bit with that one, Sophie? So it'll be more like this. This is A, B, C, D. You just pick the correct graph. Okay. Because again, we're short on time. We don't have 2 to 3 hours that we could, if we had 2 to 3 hours, yeah, we'd make you graph a bunch of these and figure everything out. But yeah, we just don't have that time. So I'll go through. What if I do this one? One more real quick. Let's do negative x plus 3 to the third. Minus 1. All right, so we know it's x to the third. Now, but again, if it's now, and this is kind of where you can go back to your end behavior. If we know it's x to the third and it's a negative x to the third, what's the end behavior have to be? Yes, it's the opposite of this one, correct? Because this was a positive x to the third. The right side up was left side was down. So this one, if you even know the end behavior before you do anything, you know it's got to look something like that. That the left side's going to be up and the right side's going to be down. It's just a matter of getting it in the correct place. So if we were doing this one back here, this would be another one where, again, you've got 4 different options. Some will be positive, some would be negative. You just got to figure out where they would be. So let's see if we can get this over here. I think we can. All right, so we know we're going to go 3 spaces to the left and 1 space down, okay? And because the negative in front, that's the reflection, correct? So that's where we get that reflection over the x-axis, which basically means we're just going to flip it upside down. So it's a reflection over the x-axis. Which again just means you're spinning it upside down. Everything that was up is now down. Everything that was down is now up. So again, we're going to go 3 to the left. 1, 2, 3. We're going to go 1 down. And instead of it being this way, now it's going to be that way. Okay. And again, they should give you a mark here to let you know where that middle. Now, they may give you another point that's here, another point that's here, but they should give you a mark that's here that you can go back and figure out what this point is. That would be at -3, -1. So you've got an idea of exactly where they're going to place this thing. Okay. So everybody all right with those graphs?
So you only replies when it's negative.
Yeah, if it's negative, so like if it had been negative x to the fourth, instead of it being like this for positive, it would have been like that for negative. Just like it would have been with x squared. So yeah, so the negative in front means you got to reflect it. Okay, now here's where they kind of throw some things at you, and they make this harder than what it is. They talk about, they tie it in with symmetry. But this is one of those things where they make it a lot harder than what it is. Even functions. Now I'm going to let you just kind of see the definition they've got here. A polynomial function p of x equals a to the n, x to the n plus a to the n minus 1 to x to the n minus 1 power plus blah, 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 till you get to your constant term, plus 2, minus 3, that kind of thing, is an even function if it's symmetric about the y-axis, and it's an odd function if it's symmetric about the origin, which is the technical math way of doing this. Now, do you want the easy version? Okay, here's the easy cut and dry version. Even functions have even exponents. Odd functions. Anybody want to take a guess? Imagine that, yes. Have odd exponents. If it doesn't have an exponent, then technically it's not a polynomial function. That would basically just put it back. That'd be a constant function, so it's not a polynomial. So in that case, it'd just be a straight line. If it's got a mix of even and odd, sometimes they call it neither. Well, if it's neither, it's got a mix of even and odd power. Okay, so sometimes on these, they like to make things sound a lot more difficult than they are. But this is one of those things that if they give you an expression and ask, is it even, odd, or neither, it's really easy. You look at the exponents. If they're all even exponents, it's an even function. If they're all odd exponents, it's an odd function. And if it's got a mix of even and odd exponents, it's neither one because it's got a mix. It's a mix of those two. Now, the one thing that they kind of tie in with this one, if you have even functions, even functions have symmetry about the y-axis, or what's been better to say y-axis symmetry. My bad. So even functions have y-axis symmetry. Because think about when we did x squared. That if you went back and drew the vertex and you drew the axis of symmetry, which again, that's the name of it, right? Axis of symmetry, that everything here to here was equidistant apart. And whether you do that with x squared or if you did it with x to the fourth, where it came to the bottom and then just flattened out a lot more and then did something like that, it still had symmetry. So anything that's got an even function is always going to have symmetry to the x or the y-axis because it's going to be equally spaced out along the y-axis as you move up through this thing. If it's an odd function, it's a little bit harder to say what it is, but anyway, it's not quite as easy as saying just y-axis symmetry. This one has symmetry with respect to the origin. And sometimes they say, all right, just for short, we'll say that it has origin symmetry. But it's one of those things that you can't really shorten that one up. Y-axis symmetry with respect to the y-axis, it's a lot easier to say it's y-axis symmetry. Sometimes with odd functions, they may say origin symmetry. Now, what that really means when they talk about that one is that if you plug in a negative number, you get a negative answer. Where, like even symmetry, if you plug in a negative number, you always get the same answer back. Whether you plug in a -2 or a +2, you get the same answer either way. If it's odd functions, if you plug in a -2, then it changes the sign of the answer at the end. So it's kind of one of those things where basically it's that one. So that if you have, well, if we went back to x to the third, that if you plugged in, just to kind of give you an idea here. Oh, mine messed up there. Oh, hang on, messed that one up. So, and you don't necessarily have to write this down. Let me just kind of show you that. But if you plugged in 1, then your y would be 1 to the third, which would just be 1. So order pair would be 1, 1, right? If you plug in -1, if we do -1 to the third, that's -1. So that gives you the point -1, -1. And origin, with respect to origin, basically says, okay, if you change the sign of the x value from positive to negative, you're also going to have to change the sign of the y value from positive to negative. Same numbers, but it's just going to change the signs on those. If we plugged in 2, that's 2 to the third, which is 8. And then with symmetry says, okay, if I plug in -2, I don't have to work this thing out that this is -2. If I change this sign, I'm also going to change that sign. And that's what respect to the origin means, is that if you change the sign of x, you're also going to change the sign of y as you plug these numbers in. So basically, when they talk about respect to the origin, if this is at 1, 1, it's here, then basically you could go almost like drawing an axis of symmetry here. Basically, you can go on the other side of it and put the same point that's here. Okay. And somebody may go, all right, well, what if we were graphing this thing and we didn't have any symmetry? That would be like the problems we were doing yesterday, how we graphed the points and then we had all those turns in the middle that when we were going to do something that didn't have symmetry, that yesterday we found out like that it had three, maybe it had 3 solutions, had one here, it had one here, and it had one over here, and it would come in and do something like this. If you've got a graph that looks something like that, there is no origin symmetry when it comes off to that part of it. Because the points just don't always match up exactly where it should be. Because again, this one might be exaggerated a little bit. Maybe better if we did something like this. That this point that's here is not going to match up with this point that would be over here, kind of thing. Or this point that's up here wouldn't match up with this point that would be down here, kind of thing. So that's kind of the visual image of what you want to think about. Is that, okay, if I've got a point that's, if this point was at, I'm trying to think what this would be here. If this was like at 6, 2, you should have another point that would be at -6, -2 that would match up with it, that would be down here. And it may be that some points do, but all the points would have to match up for it to be that way. Okay, so here's an easy example. So graph-wise, you just kind of look at it, and as long as it looks like just your basic parent function, then there's a good chance that you've got symmetry. You might have to check one of the points to just make sure that. Now for this one, if you check this point that was here, if we check the next point that would be here, I think that point would be at. If this is at what, 2, 4?
35.
Yep, this next point would be at 3, 5. So according to the symmetry thing, is that if this is at 3, 5, we should have another parent point that would be at -3, -5. And if you got a graph like this and you're not really sure, that's where you have to plug this point in and see, okay, if I plug in -3 and -5 for x and y, does it get this number? If you plug in -3 here, you'd have that. So you'd have -5 to the third plus 4. And we're running over here, just kind of scribbling. If you do -5 cubed, that's -125 plus 4. Is there any way that's going to equal -5? Because it's -125 plus 4. In that case, that's not going to equal. So if that's the case, then that doesn't have symmetry. And that's kind of what they want you to see, that if you change this number from positive to negative, you just should change this number from positive to negative as well. In that case, that's not the order pair that would work, so that won't have symmetry. So if you start shifting it around, you're not going to have symmetry, more than likely. That's really what it comes down to. Okay.
So what did you get 3 minus 2?
Oh, we were just saying that if we were graphing this one, if they asked if this graph had symmetry, we know that this point would be at 2, 4. If we found like the next point up and to the right here, it would be at 3, 5. Okay. If it's got symmetry, then we should have the same point at -3, -5. So then from that point, we plug the -3 back in here, and then we work it out. And if the answer equals -5, it's got symmetry. But if we plug in -3, it's negative 3 minus 2, which is negative 5. If we cube negative 5, that's negative 125. Plus 4 would be negative 121.
Yep.
So it's not 5, or it's not negative 5, so then in that case it wouldn't have symmetry. Okay. All right, now here's where they get a little bit easier, though. They're just going to ask you from a function, is this even, is it odd, is it negative? All right, 3x to the fourth minus 18. X squared. What are exponents? 2 and 4, right? Both even. So guess what? It's a even function. Woo, there we go. All right, what if it is 6x to the fifth minus 2x to the third plus x? All right. Now, technically, x doesn't have what is the understood power on x?
1.
That's a 1. Don't forget that. Sometimes people just blow past that. You got to remember that. They're all odd, so guess what? It's odd. All right, we get a little sneaky on you here. 4x to the third plus 2. All right, we have x to the third is odd. What power is on the 2? There's nothing, right? So there is no power. So technically, that would be x to the 0 power, right? Because there is no x there. So if this one's odd, it'd be okay that 0's even? That would technically be a neither. So that's the only tricky part that you got for these, is that if you have a constant, if you've got a number that's a constant, you've got to assume that that's going to be a 0 power. So if we have 8x to the 6 plus 2, then we're okay, right? Because x to the 6th is even. Technically, this is 2x to the 0 power. 0 is also even, so in that case, that one would be even. Okay, so that's as far as they go, everything else is really straightforward. It's just if you have a constant term, just got to remember that constant term is technically x to the 0 power because there is no x there. So technically that's x to the 0 power, and 0 is considered an even number. So, okay. Let's see what else we got. We got even, odds, and neithers. We got our graphs. Got the basic shape. So